So last video we talked about the dendrochronology. So this chronometric technique is the most precise dating tool available to archaeologists who work in areas where trees are particularly responsive to annual variations in precipitation, such as the American Southwest, developed by astronomer A.E. Douglas in the 1920s. Dendrochronology, or tree ring dating, involves matching the pattern of tree rings in archaeological wood samples to the pattern of tree rings in a sequence of overlapping samples extending back to thousands of years. This cross-dated sequence, called chronologies, vary from one part of the world to the next. In the American Southwest, the unbroken sequence extends back to 322 BC. So, when an archaeologist finds a well-preserved piece of wood, say a roof beam from an ancient penthouse, dendrochronologists prepare a cross-section and then match the annual growth rings on the specimen to those in the already established chronology to determine the year the tree was cut down. Other biological techniques include the typing of midget and beetles assemblages on land and disatoms in lakes and the ocean that are often temperature and moisture dependent, and the analysis of plant microfossils, leaves, and seeds from pack rat midden in the arid southwest United States. Geomorphological methods include the mapping of former lake shorelines that indicate past weather budgets and of glacial moraines and periglacial features that indicate past ice extent. There is abundant evidence in many areas for variations in sea level during the Quaternary. This included former coastal landforms now standing above present sea level, such as former beaches, deltas, spits, and coral reefs. Evidence for sea level change can also be found offshore in the form of submerged landforms. Mapping of such features enables the positions of former coastline to be established and the vertical range of sea level variations to be estimated. It has long been recognized that landforms of glacial deposition and erosion are important paleoenvironmental indicators. When carefully mapped, they reveal a great deal about the extent, thickness, and behavior of former ice masses. The direction of ice movement at both local and regional scales, and the nature and pattern of glacial retreat. In some cases, the information may be used to reconstruct the configuration of the former ice sheet or glacial surfaces, and to enable former ice volumes to be estimated. Comparisons with present-day glaciers, where a close relationship between glacial behavior and climatic parameters has been established, enables inferences to be made about former climatic regimes. This evidence is a key element in the development of computer models of the geometry of former ice sheets and glaciers. The history of Quaternary is immediate intimately connected with variations in the Earth's orbit about the Sun, the axial tilt of the Earth, and the position of the Earth at the spring equinox. The path of the Earth around the Sun is slightly elliptical, and the degree of this orbital eccentricity varies over about a 100,000 years cycle. The axial tilt, formerly known as the obliquity of the elliptical, varies over a 41,000 years cycle. Finally, the position of the Earth at the spring equinox varies. The precession of the spring equinox, which alters the timing of the minimum perihelion and maximum aphelion, Sun-Earth Sun-Earth distance, approximately over 21,000 years due to the combined effect of precession and orbital eccentricity. Currently, perihelion occurs on January 3rd, when the Earth is 5 million kilometers closer to the Sun than on July 4th. Aphelion, this distance effect causes of the Earth to receive 7% more solar energy at perihelion than the aphelion around 10,000 years ago, when the Earth was closest to the Sun in July. Summers in the Northern Hemisphere were warmer than now. In 10,500 years' time, perihelion will again be in July, making northern summers warmer, especially in the subtropics. So until about 0.8 million cold intervals had a 41,000 years. 41,000 periodically coincide with the period of variation of the Earth's axial tilt or obliquity, which varies between 22.1 and 24.5. It is currently 23.5. The obliquity effect is equal in the two hemispheres, and its intensity increases poleward. There is increased seasonality when the tilt is larger for unknown reasons. After 0.8 million, the periodic switch from 41,000 to 100,000 coincide with the eccentricity of the Earth orbit around the Sun. However, the fluctuations in solar radiation due to this eccentricity are too small in themselves to trigger glacial switched from 41K to 100,000K coincide with the eccentricity of the Earth orbit around the Sun. However, the fluctuations in solar radiation due to this eccentricity are too small in themselves to trigger glacial onset without amplification by ice albedo and other feedbacks. The eccentricity of the Earth orbit also shows a longer periodicity of about 400,000 years, and this may have been involved in the switch at 0.8 million years. The axial tilt and the precession of the equinox together give rise to seasonal variations in incoming solar radiation of about 10%, while the effect of eccentricity is only about 0.2%. The three orbital effects were three decadal described quantitatively by the Siberian astronomer Milankovic in 1920, but the concept of astronomical variation being a major forcing for ice ages was only given serious attention in the 1970s in the work of Vannecar, Andrea Berger, J. Hayes, and J. Bering and M. Hagestad. The last three authors identify the orbital variation as being the pacemaker of ice ages. So the Milutin Milankovic was a Siberian mathematician, astronomer, climatologist, geophysicist, civil engineer, doctor of technology, university professor, and popularized of science. Milankovic gave two fundamental contributions to global science. The first contribution is the canon of the Earth installation, which characterized the climates of all the planets of the solar system. The second contribution is the explanation of Earth's long-term climate change caused by changes in the position of the Earth in comparison to the Sun, now known as Milankovic cycle. This explained the ice ages occurring in the glacial part of the Earth, as well as the climate changes on the Earth which can be expected in the future. He founded planetary climatology by calculating temperatures of the upper layers of the Earth's atmosphere, as well as the temperature conditions on planets of the inner solar system, Mercury, Venus, Mars, and the Moon, as well as the depth of the atmosphere of the outer planets. He demonstrated the interrelatedness of celestial mechanisms and the earth sciences and enabled consistent transition from celestial mechanics to the earth sciences and transformation of descriptive sciences into exact ones. So this scientist, Milankovic, was born in Croatia and then part of Austro-Hungary in 1879. After an early career as a civil engineer in Vienna, he was appointed professor of applied mathematics in Belgrade in 1909. Interned during World War I in Budapest, he was able to work on the mathematical theory of climate and published a book on this topic in 1920. Wow, that's nice. He continued to work on the relationship between solar between solar radiation and the Earth climate, and in 1941 collected his work together in a book published in Siberian that was translated into English in 1969 under the Little Canyon of Insulation of the Ice Age problem. Then he died in 1958, almost 2 decades before his theories on the role of astronomical variations in global climate change became widely accepted by meteorologists. So, the Milankovic cycle described the collective effects of changes in the Earth movement on its climate over thousands of years. The term, named after Siberian geophysics and astronomer Milutin Milankovic in the 1920s, he theorized that variation in eccentricity, exaltitude, and precession of the Earth orbit resulted in synchronical variation in the solar radiation insulation reaching the Earth, and that its orbital forcing strongly influence on climatic patterns on Earth. The Earth orbit varies between nearly circular and mildly elliptical. Its eccentricity varies. When the orbit is more elongated, there is more variation in the distance between the Earth and the Sun and in the amount of solar radiation at different times in the year. In addition, the rotation tilt of the Earth, its obliquity, which causes the seasons as the Earth revolves around the Sun, changes slightly. A greater tilt makes the seasons more extreme. Finally, the direction in the fixed stars pointed to by the Earth axis changes axial precession, while the Earth's elliptical orbit around the Sun rotates axial recession. The combined effect of the two